Aha! There's one. Let's see here. Oh, bless you. Let's see. I need to put this back over like that. Here we go. Picks up as much possible. Okay. And here. Okay. That makes 3 of us. Let's see. All right. Okay, Tyler, you're up to date with your labs. It's good. Julianne, I'm missing molecular weight of an acid. And then the Dumas method's not due till next week.
Now, are we having a
Say again?
The weight of the acid one,
Mm-hmm.
I'm still trying to finish up.
Okay.
And the one before that I had submitted on Blackboard. I don't know if you got
Right.
that one.
I got that one. Calorimetry.
Yes.
Got it. Your question?
are we having a final in lab? Or?
No, no final lab. I just want you to bring your lab notebook in. I guess that the finals will be fine.
Okay.
Yeah, bring your lab notebook in. So I can check that out and give it a final. So we'll have on the 8th, how many days are in this month? 30 days. So tomorrow's the last day of this month. Wednesday's the 1st. So Wednesday, so we'll have our final test. It's not an exam. I mean, it's an exam, but it's not the final exam, right? We don't have a final in this one.
So our exam is Wednesday?
Yeah, on the 8th.
Not this Wednesday.
No. The Wednesday the 8th in exam week.
Okay.
That's right. I had to set the final exam aside. We had to shift something or other that ate up our final exam.
I also have 2 more questions. Do you do chemistry 2 in the summer?
Not in the summer.
Not in the summer. I'll answer the question. What's the other one too?
Yeah, we'll do. They've had me the past couple of years. They've had me teaching both 1 and 2, both semesters.
Right.
And I think the primary reason for that is to keep the cohorts coming and going through MLT.
Well, see, that's what I was going for, and the only other program I need is chemistry 2, or not program, requisite is chemistry 2, but I don't. They say you can take chemistry 2 and the MLT program in the fall, but I don't want to overload myself with like chemistry and the program. So I'm probably just going to wait to the following fall. That's why I didn't know if you had offered it.
No, I've had students do that and do them both at the same time.
I'm raising kids by myself. And,
yeah.
It'd be easier just the way. If I want to do it, I want to do it right, you know.
You got to make those calculations, you know. Okay, well, time's a wasting. Wednesday, and we don't have any more labs, do we?
I don't think we do.
We did our last one already, do my method. Yeah. Okay, so Wednesday, we'll just come in and do some more review if you need it. And that'll get you ready for the last exam. Okay, so let me pull out my copies. And we can start talking about covalent bonding. Let's see. There are some problems in here that are not quite kosher. You have any trouble with number 8? Number 8 says tetracyanoethylene has the skeleton shown below. So the trick is to find the Lewis dot structure. Then you can tell how many of the atoms are sp2 hybridized. First of all, let's just put over here on the side. This is something you might want to do on the test. First thing you walk in, just on the side or on the back of a page, write down this little scheme. So if you have hybridization, in this column, and electronic geometry in this one, tetrahedral is going to be sp3 hybridized, because tetrahedral requires 4 equally spaced bonding orbitals. And you need 4, so there's 1 and there's 3 more, that's 4. Okay? So sp2 has 3 equally spaced, and 3 equally spaced is Trigonal Planar. Okay? Then you can have sp hybridized. Actually, I did these backwards. That's okay. If you have 2, that has to be linear. Okay? So what if you need 5? We have 4 up here, but if you have 5, there are no more p's to choose from, right? There are only 3 p's. So our 5th one has to come from d's. So dsp3 gives you 5, which is Trigonal. Yeah, Trigonal Bi-Pyramidal. Remember that one where you have a triangle base and then you have something up here and something down here. Like that. So 1, 2, 3, 4. 1, 2, 3, 4, 5. And then you have the central here, and it's bound like that, like that, like that, like that, like that. If you have something in each one of these positions. The reason I said electronic geometry is one of these positions might be occupied by a lone pair. Okay, that's possible. So what's the other one possibility? If you need 6, D2sp3 is octahedral. It's just like this one, only instead of a triangle, you have a square. Right? Okay, so that gives you 6 positions. 1, 2, 3, 4, 5, 6. Now, if all of these positions are occupied by atoms, right, then the electronic geometry and the molecular geometry are the same. So if you have molecular geometry that's the same as all of these, then we can talk about bond angles. Right? Tetrahedral bond angle, there's only one possibility, 109.5. Okay? Trigonal planar. What would the bond angle be to trigonal planar? Well, if you look at it this way, an isosceles triangle, the bonds are here. Right? So in order to have 360 degrees all the way around and 3 of them, that's 120 degrees. Bond angle. It's the only possibility. How about linear? That's the easy one. 180 degrees, right? Because if you have something here, and then you have something there, 180 degrees. Trigonal Bi-Pyramidal, I shouldn't have erased that, should I? So we have our central atom here, like that. So this angle, bond angle from here to here, is 180 degrees. This bond angle here, 90 degrees. And this bond angle from here to here, let's try a different one. Let's say from here to here is 120 degrees. So it has 3 possible angles. How about octahedral? We draw our square, right? And then we put something here, and then we have that in the middle. There. Okay, so here we have possibility of 180 degrees, like that. Here, if we come down here and then over to one of these others, that's 90 degrees. But if we come from one of these, like that, that's 90 degrees. So 180 and 90 degrees are the only 2 possibilities for octahedral. Okay? So that would be a good little, I don't know, table to memorize and scratch down on the back of the test before you start taking it, just in case you need it. Oh, now let's go back to number 8. That's where I started. So, what's not fair about this? Well, the skeleton is given like that. Okay. But the name actually tells you what parts are attached. Tetracyano. Cyano is this right here, carbon nitrogen, and it's always triple bonds. See, and you're not given that in this class, right? So that wasn't a fair question. But if we look at this, nitrogen has how many electrons? Valence electrons. That's 5, right? 1, 2, 3, 4, 5. 5 valence electrons, and 3 of them are occupied in this triple bond. 1, 2, 3. So that means we have 2 left over. Okay. 2 left over. So nitrogen is satisfied. 2, 4, 6, 8. 2, 4, 6, 8. That carbon's good. All of these carbons are good. These 2 carbons are not. But each carbon has 4 valence electrons, and it's only used 1, 2, 3 of them in those bonds. So we have 1 extra here, we have 1 extra there. They make a double bond. So that's what the Lewis dot structure should look like. And there are no hydrogens there. So how many of the atoms are sp2 hybridized? sp2 hybridization gives you trigonal planar. So if you go back to the VSEPR model, where you say how many groups do you have, and that tells you what your structure is. Well, 1, 2, 3 groups means trigonal planar, right? And trigonal planar means sp2 hybridized. So that one is trigonal planar, that one is trigonal planar. So you have 2. What's the hybridization on this one? It's linear. Has two groups, right? So it would be sp hybridized. So these four are sp hybridized. And all the nitrogens are sp hybridized also, because the electronic structure is 1, 2, which means linear. But to answer the question, for A is A, 2. So you have 2 sp hybridized, sp2 hybridized. Now what does that mean for the actual molecule? Well, the sp2 hybridization gives it 3 equal hybrid orbitals, right? 1, 2, 3. And these 3 give you 3 sigma bonds, right? 1 sigma here, 1 there, and 1 there. So that double bond, that extra bond there, is a pi bond. Now, you can only have 1 sigma bond between atoms because it's on axis. Everything else has to be pi because they're off axis. But you can have 2 of them. This one only has 1. Where does that pi bond come from? Well, if we hybridize 2 p's and 1 s, remember there are 3 p's, x, y, and z. So there's an unhybridized p here and here. They overlap. That gives you the double bond, the pi bond. If you only have an sp hybridization in the linear molecule, so down here, you've got a sigma here and a sigma here. So you have 2 of these for their sigmas. And then you have unused, say a y and a z p, to give you overlap for a pi bond here and a pi bond here. So this is a sigma, this is a pi, this is a pi. Okay. As a practical matter, if you have a single bond, it's always sigma. If you have a double bond, 1 sigma, 1 pi. You have a triple bond, 1 sigma, 2 pi's. So if you press for time and the answer, and that gives you the answer, then you don't have to go through all this. But that explains why. Okay, are there any, I've been talking for a while, are there any questions that are burning a hole in your head? I'll look for any other, well, there's another one. Got any problems, or do you want me to talk about number 11?
You can go number 11.
You have what?
I said you can go number 11.
Okay. That's another one that we didn't hash out in class. That's organic chemistry. Those molecules. So here's 11. And we've got this one. That one. And that one. This is Roman numeral 1, 2, 3. And this one has C6H6 as its molecular formula. This one has C6H8, and this one has C6H10. Okay, this one's got 3 double bonds. This one has 2 double bonds, and this one only has 1 double bond. Okay, organic chemistry convention. We don't wrap carbons in. Anytime you have an intersection like that of 2 lines, that's a carbon. Carbon, 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 carbon. So there's 6 of them. We don't write the hydrogens in either, because every carbon can have 4 bonds. Right? This carbon has how many already? 1, 2, 3. So it's got room for 1 more bond, and that's the hydrogen we didn't write in. Same here. 1, 2, 3, so it has room for another. So that means each carbon can have one hydrogen in this molecule. That's why there are only 6. That's benzene. For this one, that one can only have 1, 1, 1, 1. But these can have 2. So you have actually, from this one as your starting point, move over here. Now you can have 1 there and 1 there. So that's why you have 2 more hydrogens in this one. Right. And for this one, do the same thing. So now you have 2 more other possible hydrogens. Now you have 10. Okay, the question is, which molecules have at least one carbon atom that is sp hybridized? So what do we mean by sp hybridized equals linear? Can we get a linear bond out of any of these? No. Right? There's no way to get a linear bond out of any of these. Not in a cyclic structure. So that can't happen. What is the hybridization in these, actually? There's 1, 2, 3 here. sp2. They're all equal. All of them are sp2s. Right? Trigonal planar. 1, 2, 3. Now there's an unused p. Remember, sp2 gives you 1 extra p that's not hybridized. That's where the double bond comes from. Right? In actuality, benzene, you don't put a double bond here. It's actually smeared out over the entire molecule. That's what makes benzene so stable. Because when you smear those electrons out, give them more space, they're more stable, you get a stronger bond. Actually, you get stronger, 6 stronger bonds. 1, 2, 3, 4, 5, 6. So benzene very often is written like this. Or it could be like that. Because each bond has partial double bond character. For this one, these, each one of these has 1 hydrogen, right? But these have 2. So each one of these is sp2 hybridized, right? Trigonal planar, 1, 2, 3. But each one of these is sp3 hybridized because it has 4. 1, 2, 3, 4. And you transfer that over here. Only these 2 are sp2 hybridized, and the rest of them are sp3 hybridized. Okay. That wasn't part of the question, but I couldn't resist. Okay, that was number 11. Markers are starting to crap out. I haven't used this one today. Maybe it'll work better.
Cody said, once you got it working, that he's trying to get logged in, but he's logged out.
I see him. Okay. There he is. Okay, let me mark him present. So that's 2, 3, 4, 5. 1, 2, 3, 4, 5. So we got 5 attendees at present. Okay, any others? I've been making things up as I go along here. Let's see. The best way to determine hybridization is to go back to your VSEPR model and say, how many groups do you have around this central atom? And that'll tell you what the geometry is. And then you can use this to give you the hybridization that's required. I think that'd be the most efficient way to use it. So if you memorize this one and then spit it out on the back of a page before you even start to take the test, you'll be in good shape as far as this stuff goes. Any question that refers to hybridization related to geometry, that's the way to go. Okay, I see some mention of molecular orbitals in there. Let's get those a little later. Let's try. How about okay. All right, those tables toward the end and the fill in the blanks and stuff, those are molecular orbitals. Oh, here we go. How about 59 and 60? Let's be sure and get those under our belt. And 61. Let's do those. $59. Does that show up? Yep, that shows up pretty well. Explain the concept of delocalization of electrons in SO3. Indicate how this idea relates to resonance. Okay, first of all, what's delocalization? It's like that concept I was talking about earlier, smearing the electrons. You spread the electrons over many different atoms, possible Lewis dot structures. So let's look at SO3. How many electrons do you have? We're going to draw the Lewis dot structure. Right? Oxygen and sulfur are in the same family. So each one has 6. So 4 times 6 is 24, right? 24 electrons. So if we have S, 3 oxygens, that's 2, 4, 6. That's 18. Okay, now we have to put 18 electrons right here. So 1, 2, 3, 4, 5, 6. 6 times 3 is 18. So if we put 6 more around each oxygen, we've used them all up. Okay? But sulfur doesn't have an octet yet. All right, so how do we make an octet? We steal 2 electrons, right? Make a double bond. So if we do it from here, we get this one. If we steal it from here, we get this one. And if we steal a pair from here, not all at the same time, just structures, then we get this one. Okay. Here we go. So those are all valid Lewis dot structures for this molecule. What we would normally have to do is say, all right, resonance. So these structures resonate backwards and forwards. We can't tell which is which. So, how would we represent this as a delocalized molecule? Well, we would do like that benzene. We would give every bond a partial double bond character. that would smear the electrons over the entire. So one way to represent all three of these together is to say this and just give each of those bonds a partial double bond character. The problem is, what do you do with these lone pairs, right? Localized electron model says they have to go somewhere. But when we do this, we don't know where to put them, right? So they get here too. So it's 2, 4, 6, 8, 10, 12, 14, 16. So 16 electrons get smeared out also over the entire thing. This does add to their stability, though. Anytime you can give electrons more
How many
room.
does that have on there?
I'm sorry? They should be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Because you have 16 electrons here.
So how would you want that worded for the answer?
Yeah, do you want all of this?
No, just explain it this way. Normally, with the Lewis dot structures, what you do is you share a lone pair from one of the oxygens. And since every oxygen is equivalent, then we represent the sharing with resonance structures, 3 equivalent resonance structures. Okay, that's the Lewis dot structure way. When we delocalize the electrons, then we smear them over all of the 3 bonds and give each bond a partial double bond character. These are 2 equivalent ways to show delocalization: resonance or partial.
So when you delocalize the electrons, you smear them and give them all double bond characteristics?
You give each of the bonds partial double bond character.
Okay, partial.
If you're going to give one of the bonds a full double bond character, then the other 2 have to be single. And at that point, then you have to introduce resonance. Right? If you're saying this is a full double bond, then this one's just as good as that one, and that one's just as good as this one or that one. Then you got to say they resonate. And when they resonate, you're delocalizing the electrons, right? Because they have to shift like that. They have to shift as you move from one resonance structure to another. That's the concept of delocalization. I think in your books, it may show you something like this and give you the electron density as sort of a, like that. I don't have my textbook
Could
with me.
we draw that?
Yeah. Yeah. But you need to explain what it means.
Yeah.
Right, drawing a structure like that helps add flesh to your words.
Yeah.
Yeah. Okay. Erase this.
I should leave this for the right side.
Leave this?
Yeah.
Oh, okay. Well, I'll leave that too.
But I haven't wrote that down.
Okay, I'll give you another minute. Delocalization is sort of a stepping stone to molecular orbitals. because molecular orbital takes that concept to its logical conclusion. Molecular orbitals are orbitals that are assigned to the entire molecule. They're not localized to any one atom. And so when you go to molecular orbitals, then you can discuss electrons in these bonds in terms of the entire molecule.
What about 60?
Yeah, I'm going there next.
Okay.
You can erase that now, good.
Okay. All right, so 60, we want to complete this table. Let's see, we have molecular structure. We have hybridization. We have bond angles. And we have possible examples. Okay. For these three molecules, A, B, C, all right, our starting point is hybridization for A. It's given, sp3 hybridization. So what can we tell from sp3 hybridization? The molecular structure would be tetrahedral. And we have to assume that every position in the molecule is occupied by an atom, no lone pairs. Right, in order to have molecular structure that way. Right. If we had something like ammonia, it's only got 3 hydrogens, right, plus a lone pair, then the electronic structure would be tetrahedral, but the molecular structure will be trigonal pyramidal, right, because we cover that up and we have these 3 hydrogens sticking out. So that's one thing that we have to assume here, is that molecular structure means that every position is occupied by an atom. That being said, what's the bond angle? Well, 109.5. What's an example? Well, you need a central atom plus 4 bonded to it. Good example? Methane. Right. Another example, dry cleaning fluid, carbon tetrachloride. Right. That gives you 4 bonded atoms to the central carbon arranged in a regular tetrahedron. And in order to give that, you need 4 equal hybrid orbitals constructed from 1s and 3 p's. That was the example I gave in in the PowerPoints, right, at the very beginning of that lecture, was methane. Methane was a problem because we knew it had a regular tetrahedral structure. We proved it by alternate methods, but we couldn't prove it by 2 electrons in the s orbital and 2 electrons in the p orbital, right? The localized electron model would not let us produce a tetrahedral structure using 1s and 2 p's. So we had to hybridize it. Okay. Next, it says that molecule B has 2 more effective pairs around the central atom than molecule A. So it has 2 more pairs. That's 2 bonds, right? 1 bond is a pair. So 2 electron pairs around there, they need 2 more orbitals to occupy those. So to hybridize that, we need 2 Ds because the S's and P's are all used up. We have to go to Ds then. So what's the structure here? 2, 3, 6. That's octahedral. Right? And the bond angles are going to be 180 and 90 degrees. Okay? So what's an example there? Well, we need 6 attached to a central atom. This is a good example. Sulfur hexafluoride. So you've got 6 fluorides bonded to sulfur. That gives you the structure. C then is said, C consists of 1 sigma bond and 2 pi bonds. So if that molecule has 1 sigma and 2 pi's, what does that mean? That means 1 sigma in the middle. Oops, that's not good. 1 sigma, 2 pi's. Triple bond. The only thing you can get out of a triple bond is linear. So this one has to be linear. And that means sp hybridized. It can only be 180 degrees. And then what are the possibilities? Well, carbon monoxide works. Acetylene works. Cyanide works. Each of these molecules has a triple bond. Triple bond here. Actually, a triple bond between the carbons, which leaves 1 bond on either side for the hydrogens. Let me just draw it. Like that. And cyanide is, let's see, like that. 2, 4, 6, 8. But it has a charge. Okay. So those are examples. Okay. Move on to 61. I wonder if we need to. Yeah, we can do 61 now. Molecular orbitals. Maybe we ought to do a simpler molecular orbital first, rather than get into dinitrogen and dioxygen. We'll come back to that one. Let me find a simpler one. How about, I'll go grab coffee real quick. Well, let's do review first. Molecular orbital. Let's take the very simplest one possible. Dihydrogen. Okay? So if this is our energy on this side, then we have 1 hydrogen here, 1 hydrogen here. Start off with the atomic. So this hydrogen only has a 1s orbital. This one only has a 1s orbital. And each one has 1 electron in it. Okay? first rule of molecular orbitals is when you make molecular orbitals, you have to have the same number of molecular orbitals as the atomic orbitals they came from. So we have 2 here. That means we need 2 molecular orbitals. One's going to be higher energy. One's going to be lower energy. This one's going to be sigma derived from 1s orbitals. This one's going to be sigma star derived from 1s. So what's the difference? This one's a bonding orbital. That one's an anti-bonding orbital. So now that we've got our orbitals composed, where do the electrons go? We've got 2 electrons. So we fill them in just like we did before with Hund's rule. Lowest energy first. And for the degenerate orbitals, you pair them up if there's only 1. If there are more orbitals at that level, then you put up spin in each one until you run out of orbitals, and then you go back and start pairing. So this is dihydrogen with 2 electrons in the sigma 1s orbital. Okay? So now what's the bond order? Remember the bond order? You add up the electrons that are in bonding orbitals, in this case 2. You subtract those that are in the anti-bonding orbitals, 0, and divide by 2. That's 1. So the bond order of dihydrogen is 1. What if we made an ion out of this? Let's say we subtract an electron. Right? So that would make 1 positive, right? Take away a negative, leaves us with a positive. So that means now we only have 1 electron in a bonding orbital. What's the bond order for that one? 1 minus 0 divided by 2 equals 1/2. So we have weakened the molecule by removing 1 electron from a bonding orbital. What if we go the other direction? Let's say we add an electron, like this, like that. So this would be negative. We add an electron. What's the bond orbital of this one? Bonding order. 2 minus 1 over 2 equals 1/2. So in this case, subtracting an electron or adding an electron weakens the bond. That doesn't have a number. I just started talking. Try to get us in the molecular orbital frame of mind. Now we can look at actual problem numbers. Let's see here. Like 15. The fact that O2 is paramagnetic can be explained by, okay, first of all, let's remember what they mean.
It says 15, you said?
Paramagnetic equals attraction to magnetic field. Whereas diamagnetic equals no attraction. Okay, that's the practical application. If you take oxygen and take one of these big horseshoe magnets, you've seen those? You've seen pictures of them maybe. Huge horseshoe magnet with a gap in it like that, and the magnetic field in there is a monster. If you pour liquid oxygen into that gap, it'll sit right there in the magnetic field because it's paramagnetic. It responds to that magnetic field. Okay. If you do nitrogen, I think I'm right there. Same thing, it just goes right on through. Doesn't even stop. No attraction to that magnetic field. Now, what's the explanation? Well, in order to be paramagnetic, you need at least one or more unpaired electron. Okay? Why? Because you can look at electrons as little spinning magnets. Right? They're doing like that. And if they're paired, then the other one is going the other direction. They cancel one another out, right? So if they're all paired, you get no response to the magnetic field. But if they're unpaired, then this one presents a magnetic moment of its own. As that electrical charge spins, it creates a magnetic field around itself. And that's what allows it to respond to that magnetic field. So what you're looking for as a practical matter, you're looking for unpaired electrons. Paramagnetism and diamagnetism were two observed characteristics of elements that could not be explained with a localized electron model. It just fell apart. The only way they can be explained is with the molecular orbital model, because then we can identify accurately the paired electrons, the unpaired electrons, which ones do have, which ones don't have, and they correspond exactly with paramagnetic or diamagnetic as a consequence. Okay, so let me get back to, let's see, which one did I say?
15.
15. Here we go. The fact that O2 is paramagnetic can be explained by what? Okay. O2. So we have O2 here, constructed from oxygen, individual oxygen atoms. And we're just going to take their period 2 electrons. We're not going to mess with 1s electrons. They're going to be the same anyway, so it doesn't matter. So what do we have? Well, for the oxygen, we start off with 2s right here and 3 2p's. Okay. We get interaction here. From these two S's, this makes a sigma from a 2s, this makes a sigma star from a 2s. These, you can only have one sigma, right? So this sigma is made from a 2p, and this sigma star is made from 2p. Then we get this is a pi from a 2p, and had 2 pi's, and this is pi star from a 2p. Okay, so let's see if I've done that correctly. We should have the same number of molecular orbitals as atomic orbitals we started with. So there's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got the right number. Question is, are they in the right order? Well, for oxygen and fluorine experience no sp mixing. So this is the order that they come with, no sp mixing. You have sigma here, sigma there, and the pi's are in between. Okay? If we had molecules that experience mixing, like nitrogen or dicarbon, then these two would be flipped. We would have the pi 2p at a lower energy than the sigma 2p. That's for mixing. This is non-mixing, right? And how do you know? Well, I'm not going to expect you to memorize those. That's why I gave you these charts in the back. They give you the order of the orbitals, molecular orbitals. So you don't have to memorize them. It's good if you can recognize which is mixing and which isn't. Let me go back to 15. Okay, so to answer this question, we say, how many electrons are in the p orbitals? Well, we've got 2 in the 1s's that we didn't use, and then the 2 p's are going to be 6 each. Right? So 1, 2, 3, 4, 5, 6. That's how we start. So we got 2, 4, 6, 12 electrons total. Now we take those 12 electrons and we put them in the molecular orbitals, lowest energy up. At this level, we pair. At this level, so that's 2, 4, 6, and then we 6, 7, 8, 9, 10, 11, 12. Right? At this level, these are both the same energy, so those electrons have to go in unpaired first. Then if you have any extras, you pair them up. But we run out. 2, 4, 6, 8, 10, 12. 12 electrons total. We had 6 here, 6 here, 12 total. So we've used them all up. So, in oxygen, we said it is paramagnetic. That is, it responds to a magnetic field. That's why. These are paired, they don't respond. These two are unpaired. They do respond. That's why oxygen is paramagnetic. Now, to answer the question, the fact that O2 is paramagnetic can be explained by what? The Lewis structure of O2. What is the Lewis structure of O2? That doesn't explain it, right? Because this shows paired electrons all the way around. That doesn't explain it. So A is false. Resonance. There's no resonance structure for that. That's the only valid Lewis dot structure there is. So resonance can't work. A violation of the octet rule. 2, 4, 6, 8. 2, 4, 6, 8. Octet rule satisfied. So A, B, and C are all false. The molecular orbital diagram of O2. That's it. That gives you these 2 unpaired electrons. D is the answer. Hybridization, that doesn't explain it. 1, 2, 3 means sp2. That just tells you that the electronic structure around that oxygen is trigonal planar. It doesn't explain paramagnetism. Molecular orbital theory is the only way to explain paramagnetism in oxygen. Now, while we've got this diagram up here, what if, well, let's do the bond order first. What's the bond order of O2 as we've structured here? right? So first bonding, 2, 4, 6, 8. Okay, 8 minus anti-bonding, 2, 3, 4. 4 divided by 2 equals 2. Okay, so the bond order is 2. What if we add an electron? Give it an extra electron. Where does it go? It has to go right here. So we've added an electron to an anti-bonding orbital, which makes it 8 minus 5 over 2. So that's 3.5, makes it 1.5. 3 halves makes it 1.5. What if we subtract an electron? Where do we take it from? We take it from the highest energy orbital, right? So that would be, we've taken 1 from here, so that's 8 minus 3 divided by 2. So that's 5 halves, 2.5. Okay? So adding an electron weakens the bond from 2 to 1.5. But subtracting an electron strengthens the bond because the electrons were removed from anti-bonding orbitals. So 8 minus 3 is 5, divided by 2 is 2.5. So that ion is stronger than O2. What if we take 2 electrons away? Right? So now we have 2, 4, 6, 8, and then anti-bonding 2. That's it. Divided by 2. 2 from 4 is 6, right? That makes 3. So take away 2 electrons, you get even stronger. And remember, let's see. Yeah, okay. That's it. That's what happens. Now, one thing I don't think we talked about in class was shorthand notation. But it's used in your problem set. All the shorthand notation is it takes these things right here that describe each of these bonding orbitals and the anti-bonding orbitals and just strings them out like that. So this would be, well, actually now we need to include the 1s bonding and anti-bonding. Sigma s, sigma star s. And then the number of electrons in each one. So this one has 2 and that one has 2. Then we come to this part. So this one is sigma 2s and then sigma star 2s. Each of these have 2 electrons. Then we come to sigma 2p. It has 2 electrons. Then we come to pi 2p. How many electrons can be in the pi 2p? Well, there are 2 degenerate orbits with 2 electrons each, so you can have 4 of these. And then with O2, see this is O2, not the ion. Then we have pi star from the 2p, and this is 2 electrons. So with that arrangement, we can quickly deduce that that's full means paired, 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 2 paired, 2 unpaired, because the maximum is 4. If we do like that, they have to be unpaired. So this tells us the same thing that does in shorthand notation. Now this is O2, and that's no SP mixing. N2 has SP mixing. So it's going to be, these are going to be the same. And then this one trades places over here and puts that one there before we get to this one. Okay, that's SP mixing. You just flip these two. But N2 only has 10 electrons in its valence orbital. So these are the same, but we have 10 electrons here. So 2 here, then 4 here, 2, 4, 8, 2 there. They're all paired. We don't even use that one. Okay, that's why N2 is diamagnetic. It has no unpaired electrons. They're all paired. Oh, I didn't write the number on that one, did I? That's 15. At least I began on 15. And then I did, my father says, jump on your horse and ride off in every direction. Okay. See how we're doing on time. 12:30, 1:30. Where do we go to 1:45?
Yeah.
Okay. So we got a few more minutes. Do you have another one you want to look at before we'll come back on Wednesday when you've had a chance to digest some of this stuff and talk about some others. We never got to 61, did we? And some of the others, like 57 and 56, are complicated. They look complicated. But if you use shorthand notation, you can get through them pretty quick. And how do you know which shorthand notation to use? Well, just look in the back at this thing right here. And you know how to translate the orbitals into shorthand. You just take it, lay it on its side, and then fill in the electrons as superscripts. That's shorthand notation. Okay? All right. We'll see you in a couple of days. No more labs. But you do have one lab report due next week, I guess it is, isn't it? If you haven't already turned it in. Let's see. Oh, I didn't see Sasha showed up. You should have announced your presence.
Sorry.
I'll mark your present.
Yeah, I looked at the clock and it was like 12:50 and I was like, uh-oh.
Yeah.
I got carried away baking.
So I'll convert this and post it so you'll be able to watch this tonight. If you like. Tonight or tomorrow night, whenever you have time.
Wednesday, I'm going to stop by briefly to drop off my lab notebook. I already have all the stuff copied out of it to where I don't need to have it with me when I finish the report for last lab.
Okay, that's fine.
So I'll just stop by before we head to our doctor's appointment.
Okay. All right, that's it. Bye-bye.